Hello guys, in this video I'm gonna go over how to evaluate limits using the L'Hopital rule, and we're gonna go over the rule here, and then we're gonna go over some examples like how to use the L'Hopital rule to evaluate limits. So we're gonna find the limits of these functions using the L'Hopital rule. Okay, so let's go over the rules. So first of all, let's say we got two functions fx and gx. A limit is x approaches to a gives us 0 for both of them, and both functions are continuous and differentiable at that limit value as x approaches to a. And then according to this rule, the limit of fx over gx is basically equal to limit of derivative of fx over derivative of gx. And again, so this rule works whenever you get indeterminate form. For example, you got 0 over 0, that's why I wrote limit of fx is equal to 0. So this part is 0, limit of gx as x approaches to a 0. So that gives us 0 over 0. And it also works when it is infinity over infinity, or a positive infinity over positive infinity, or negative infinity over positive infinity, all those indeterminate forms. Okay, and that's where we find the derivative of the numerator and derivative of the denominator and apply the limit. And we can keep going or keep find the derivative if, let's say, you got 0 over 0 and you find the derivatives and we still got 0 over 0 or infinity over infinity format, then we're gonna find the second derivative. So we're gonna keep going, then we're gonna go to limit x approaches to a f double dash x over g double dash x, so until we can find the limit. Okay, so let's solve some examples, then you will see how it works. Okay, so let's start with the easiest one. So we got a function that's where limit x approaches to 2. So if I plug in 2 over here, let's see what we get. So if x is 2, I got 2 raised to power 3 is 8, minus 2 times 2, 4, multiply by 7 gives me 28, plus 10 over 2 square is 4, plus 2 minus 6. So I got 0 over 0. So that means we can use the L'Hopital rule over here. So what we need to do, we need to find the derivative of the numerator and the denominator. So let's do that. So this can be written as a limit x approaches to 2. So derivative of the numerator is 3x squared minus 14x plus 10 over 2x plus 1. Okay, and now if we plug in the value x is equal to 2 here, let's see if we got 0 over 0 or if we find the limit. Okay, so that'll give me, if I plug in 2 over here, that gives me 2 times 2, 2 squared is 4, times 3 is 12, minus 14 times 2 is 28, plus 10 divided by 2 times 2 is 4, plus 1. So this is basically going to be equal to negative 6 over 5. So that's the answer. That's the limit of this function using L'Hopital rule. Okay, so let's solve this one. So if we plug in a is equal to infinity over here, so this numerator gives me infinity and denominator gives me infinity. So again, we got indeterminate form. So that means we can use L'Hopital rule over here. So again, so what we need to do, we need to find the derivative of the numerator, so which is basically equal to 1 over 2a into 2. So we are using a chain rule here, and in the denominator we got just 2a. So this is equal to limit a approaches to infinity, cancel out, this a will come to the denominator, gives me 2a square and if we plug in a infinity over here, it gives me 1 over infinity. So that means this is equal to 0. So the limit of this function as a approaches to infinity is equal to 0. Okay, let's do more examples. So this is limit x approaches to 0 and the function is x log base e of sine x. So if we plug in x0 over here, that gives me 0 into infinity form. So that does not look like 0 over 0 or infinity over infinity. Let's see what we can do over here. So limit x approaches to 0, and I can rewrite it as a log of e sine x 1 over x. So I'm going to bring this x to the denominator. Now if you plug in x0 over here, this gives me an infinity over infinity format. So I can use a L'Hopital rule over here. So what we need to do, we need to find the derivative of numerator and the denominator. So limit x approaches to 0. So derivative of numerator is a log of sine x, which is basically 1 over sine x into derivative of sine x, which is basically cos x. So we used the chain rule over there, and 1 over x, the derivative of 1 over x is minus 1 over x square. Okay, and let's simplify it. Cos x over sine x is cotangent x over minus 1 over x square. I'm gonna rewrite this, take negative out, limit x approaches to 0. I'm gonna take this to the numerator. So we got x square, and cotangent x in numerator can be written as tangent x in the denominator. Okay, so this is basically minus limit x approaches to 0, x over tangent x into limit x approaches to 0, x. So I just wrote this x square into 2 x's over here. So this part gives me 1 from the standard formula, and this gives me 0. So basically the answer is equal to 0. Okay, let's do next example. So this example will take some time, but we're gonna do it because we need to use L'Hopital rule over here few times. We need to find the derivative couple of times here. Okay, let's start with this one. So we got limit x approaches to 0. So first of all, let's see if this gives us indeterminate form. If x is 0, so in the top we got 0 minus 0 is 0, and in the bottom we got 0. So we got 0 over 0, so we can use a L'Hopital rule over here. So that means we need to find the derivative of numerator and the derivative of the denominator. Let's find the derivative of numerator first. The derivative of tangent x with respect to x is secant square x, and dx over dx gives me 1. And now in the denominator we need to use the product rule over here. So derivative of x square gives me 2x tangent x plus x square, and derivative of tangent x is secant square x. Again, x is equal to 0 over here, so we got this part gives me 1, so 1 minus 1 is 0 over 0, and this part gives me x0, so 0 over 0 format again. So we need to use L'Hopital rule again. So we need to find the derivative of numerator and denominator again. So let's do that. Limit x approaches to 0. So derivative of secant square x is basically 2 secant x into derivative of secant x, which is secant x tangent x. So we are using a chain rule over here. Minus derivative of 1 is 0. So divide it by, so derivative of this first part, so we need to use chain rule over here and here. So I'm going to write the derivative of first part, which is 2, the 2x. So gives me 2 into tangent x plus 2x into derivative of tangent x, which is secant square x. Okay, it's going to be a long problem. All right, so second here, the derivative of x square is basically 2x. I'm gonna leave secant square x as it is, plus x square, and derivative of secant square x, I'm gonna write it down from here, which is basically 2 secant square x tangent x. So 2 secant square x tangent x. Okay, and let's rewrite everything over here. So in the numerator we got 2 secant square x tangent x and divided by 2 tangent x, and 2x secant square x, 2x secant square x gives me 4x secant square x, plus this part, which gives me 2x square secant square x tangent x. So we got 2x square secant square x tangent x. And now we need to plug in x is equal to 0 again. So if I plug in x is equal to 0, the top part, this part gives me 0, and 0 here, x is here 0, x is here 0. So again I got 0 over 0 format. So we need to find the derivative one more time and see if we still get 0 over 0 or not. Okay, so we need to apply L'Hopital rule again. So find the derivative of numerator. So again we got two functions here, so we're going to use the product rule. So derivative of 2 secant square x is basically 2 into, and we know derivative of secant square x is 2 secant square x tangent x. So I'm going to write it down over here. 2 secant square x tangent x into this tangent x plus 2 secant square x into the derivative of this tangent x is basically secant square x. And same thing we're gonna do in the denominator. We need to find the derivative of all these functions in the denominator. So first of all, derivative of 2 tangent x is basically 2 secant square x plus, and here we need to use the product rule. So 4x basically 4 secant square x plus 4x into derivative of secant square x is 2 secant square x tangent x. We already found this over here, so we don't have to like solve it again and again. Just plug in the value from there or from there, plus, and here we got derivative of this function 4x into secant square x tangent x plus 2x square. Now I'm going to find the derivative of secant square x, which is 2 secant square x tangent x into tangent x. I'm gonna write it over here, plus, now I'm gonna write these two as it is, 2x square secant square x, and need to write the derivative of tangent x, which is secant square x. Okay, so this and this gives me the derivative of this part. Okay, so now rewrite everything what we wrote. So limit x approaches to 0. In the numerator I got 2 times 2 is 4 secant square x, tangent and tangent gives me tangent square x, so I got 4 secant square x tangent square x plus, and secant square multiplied by secant square gives me 2 into secant power 4x. And in the Denominator, I got 2 secant square x plus 4 secant square x gives me 6 secant square x, and this is 4 times 2, 8x secant square x tangent x, and plus 4x secant square x tangent x gives me 12 secant square x tangent x. So I'm adding this one and this one, and then I got this part. 2 times 2 is 4, 4x square secant square x tangent square x. So secant square x into tangent square x plus this part gives me 2x square. Secant square into secant square is secant power 4. So 2x square secant 4x. Okay, now plug in x is equal to 4 in this and see what we can get. So when I plug in x is equal to 0 in the numerator, this part over here gives me 0. So in the numerator I left with, and this part gives me secant 0 is 1. So this gives me just 2 in the numerator. So in the denominator, when x is 0, so secant is 1. So I got 6. And this part gives me 0, this part gives me 0 because tangent 0 0, tangent 0 0, and x is 0 here, so 0, and x is there too. So plus 0 plus 0 plus 0. So I basically got 2 over 6. So this is equal to 1 over 3. So that's the limit of this function using L'Hopital rule is equal to 1 over 3. And you see, we applied the L'Hopital rule I think 3 times, because even after finding the derivatives we were still getting indeterminate form in this problem. Okay, so you can apply it multiple times until or unless you can find your limit. Let's do one more example, and this is the last example for today's video. And I recommend you guys to practice more example by yourself too, and have question, just type a comment in the video and I can reply you back. So this one is a limit x approaches to infinity, e raised to power x plus x raised to power 1 over x. So basically we are getting here infinity, or this gives me 0 and 0, 1 raised to power infinity kind of format, I believe. Alright, let me see. Oh, infinity, infinity. So this is basically infinity raised to power 0 format. So let's rewrite this problem. This problem is a little tricky, so we're gonna play a trick over here. Let's say this whole limit is equal to a. So a is equal to limit x approaches to infinity of e raised to power x plus x 1 over x, and take log on both sides. So left hand side, therefore left hand side will turn into log natural a is equal to 1 over x log natural, I would say, e raised to power x plus x. Okay, it can be rewritten as log natural e raised to power x plus x over x. Okay, and now we're gonna find the limit. So let me rewrite it. So we got log natural a is equal to log natural I think I forgot to write the limit, so let me rewrite it. So yeah, so just type limit over here. So limit x approaches to infinity and limit x approaches to infinity. So let's rewrite it. So we got limit x approaches to infinity of log natural a, and I'm supposed to write limit over here to x approaches to infinity. Okay, is equal to limit x approaches to infinity of log natural e raised to power x plus x over x. Okay, so now if you see on right hand side, if you plug in x is equal to infinity over here, so you got infinity over infinity format. So that means we can apply L'Hopital rule over here. So according to that, we need to find the derivative of the numerator and the denominator. So let's do that. So derivative of this part gives me e raised to power x plus x, sorry, 1 over e raised to power x plus x into e raised to power x plus 1 divided by derivative of x gives me 1. So which is basically limit x approaches to infinity, e raised to power x plus 1 over e raised to power x plus x. And if you look at it again, if you plug in infinity over here, this again gives me infinity over infinity format. So that means we need to apply L'Hopital rule again over here. So limit x approaches to infinity. So I need to find the derivative of the numerator and the denominator. So this part gives me e raised to power x plus 0, and the denominator I got e raised to power x plus 1. And if we plug in x equal to infinity over here, so we're still getting infinity over infinity. So let's apply L'Hopital rule one more time. So that can be written as limit x approaches to infinity, and we got e raised to power x because the derivative of e to the x stay the same. In the denominator we got e raised to power x plus 0. So cancel out, we got limit x approaches to infinity of 1, and that is equal to 1. So this basically limit x approaches to infinity of log natural a. And the second trick we're gonna play over here is, and we know a is equal to e raised to power log natural a can be written as, because this is basically equal to a. So let's rewrite our original function, which is limit x approaches to infinity of e raised to power x plus x raised to power 1 over x, and is equal to limit x approaches to infinity, and we said assume this is equal to a over here, so this part is a. So limit x approaches to infinity of a, and limit x approaches to infinity, a can be written as e raised to power log natural a, and this whole thing can be written as e raised to power limit x approaches to infinity of log natural a. This is equal to e raised to power, and this part over here we already solved it. The limit x approaches to infinity of log natural a, this one is equal to 1. Okay, so what we got here, the limit of this part is 1, so is equal to a. So basically the limit of this function as x approaches to a is equal to just e. Alright, so we played a trick over here. We assumed this whole thing is equal to a, and then we took the limit, and we use some properties of logarithmic here, and then we use the L'Hopital rule over here to find the limit of log natural a, and then we played or used another trick of logarithmic over here. A is equal to e raised to power log natural a, and we plug in that in our function and found the limit. Alright, thank you. I hope this video will help you guys, and I always recommend please solve more more problems by yourself. That way you'll be more confident while solving the problems. Thanks for watching the video, and please share and subscribe to the channel. Thank you guys. Have a good day. Bye bye.